Alright, this is going to be my formal lab report video for experiment number 10 regarding, the identification of unknowns via IR spec. Me and my partner, Ryan Ballard, did it. Of course, unfortunately, he couldn't be here. He had a wrestling match, and yesterday we were going to do it. And when I had class, he didn't, and when he did, I didn't, so we just couldn't work it out. So he did his own, I did mine, but we got the same results, so let's just go ahead and get into it. I also have to go over and click the slide because the pointer won't work. So, first off, I want to introduce by talking about infrared spectroscopy. Of course, figure 1 up here is the actual IR spectrometer that we use to analyze the liquids, our liquid samples. Figure number 2 is another IR spectrometer that we use with the ATR adapter that we use to analyze our solids. Figure 3 here is actually an example of what a spectrum of IR spectrum would look like. This right here is an example of 1-propanol, as we can see the OH group over here, and the sp3-CH bond. We'll talk about that later though. Let's see, figure 4, which we can't see right now, is actually a salt plate. So, I don't know what we're going to see. There's a salt plate right there. Of course, we take our pipette and our liquid sample here, and we drop 1 drop in the middle, and we build with like a sandwich, and we put it on the plate, and we screw that into place, and then that's going to slide down into this one right here. Our infrared spectroscopy is the spectroscopy that deals with the infrared region of the electromagnetic spectrum. It helps us to identify certain functional groups. For any given sample, which can be a solid, liquid, or gas, we use the infrared spectrometer to produce this spectrum right here. When organic molecules absorb radiant energy in the IR region, specific bonds within the molecule become excited and vibrate. If the frequency of that incident radiation matches the specific vibrational frequency of the bond is excited to a higher vibrational state, and the amplitude of that vibration will increase, like these two right here, and that's where you get your major peaks. Structurally, different molecules will not absorb at the same energy. So, for instance, if another molecule didn't have that OH bond, this absorption right here will not be present, and you will know that it doesn't contain an alcohol. And IR spectrum displays these results, and of course it graphs down here on your horizontal axis is your wave number, which is indicated in reciprocal centimeters, and your vertical axis is going to be percent transmittance, which is just relative of your absorbance. This right here is actually absorption frequencies that you will see. For instance, like in the CH of an alkene, you're going to see it around 3020 through 3080. Of course, there's other ones. There's your alcohol right here, 3200 to 3600, and there's the rest of them that we're going to use later on in the presentation. Next, I want to talk a little bit about mass spec. We didn't really use this experiment, but mass spec is a technique that analyzes molecules and particles according to their mass. It comes in many variations, but its simplest setup is when the sample is introduced in its gas phase, and the molecules are bombarded by an electron beam, which in turn transforms these to charged particles. Of course, when it's ionized by this electron beam, a radical cation is formed, which is the molecular ion, which for this example right here is hexane. Right here it's about 86 is the molecular ion for that. It's just a molecular weight, but it's in cationic form. Due to the instability of these charged particles, however, the molecular ion will fracture into smaller pieces. So for like hexane, when this methyl fragment drops off, you're going to have the rest of the molecule with a mass of 71 right here, and you get this little peak right here. Of course, you have your n+1 peak over here, and then it continues so on. These fragment ions are analyzed according to their mass to charge ratio, which is graphed on the horizontal axis, and that's your m divided by z. And then on your vertical axis, you have your relative absorbance. Of course, the more stable the fragment, the higher the absorption will be. This right here is the list of unknowns that we were used for experiment 10. We had 10 liquids and 6 solids. Our 2 liquids were L2 and L4, and for the solids we had S5. And you literally cannot even see that, so you might as well just pause it.